Okay, I think we can start the day. Um, yeah, I will try to make a recording uh, for today's lecture and the future ones. Um, I think it's still nice to have recordings so you can have the chance to review at a later time. Um, so just to let you know that. Okay. Okay, today's lecture will be about gameplays. Yeah. This semester we move gameplays to the early part of the semester because very quickly we're going to have projects announced regarding gameplays. The formal title is called adversarial search because these are not single player games. There are many games that are single players. Okay, like you can play some puzzle games. Okay, some uh, match and delete games like Candy Crush or some Sudoku or a lot of things are single player games that you can use to kill your time, and those are very nice. Yeah, but a single player game is more like a regular search where you try to find a solution to your desired state. For adversarial search, it means there are other players. Okay. Other players who can think and make decisions in response to what you do and in response to what the environment, the state is. Okay. So, in a word, the other players are intelligent too, and they have different goals or objectives as you do. Okay, so you want to win, and the other player also wants to win as well, but you cannot both win. Okay, so either one or your it's called the adversary. Okay, the other player uh, have to compete. So that's the idea of adversarial search. Okay. Um, well, for now, I can only do the complete screen recording. Okay. So when you see the video, you're going to see some interruptions. Well, that's what I can do for now. So please just don't mind. Um, okay. So the whole topic most this week and maybe this most of next week lecture were about the adversarial search. The reason we call it search is because when you play a game, okay, you start from some state, uh, you have to make some decision on what you want to do. Okay, you have to choose a move or action. To do that, you need to think about first, if you do this action, what will happen next? And there will be some new state of the game, and then what you can do from that new state. Okay, that results from your action, and this goes on and on. Okay, so that's a search. Okay, you have to think about one action and then what are the possible subsequent actions and their results, the consequences, new states, and you try or yeah, you have to think about these things before you make a move. Of course, you can be uh, reflective as well, but most player, when you do something, you're not reflective because that way it's not very intelligent. So to have good performance, you have to think. The thinking actually is some sort of searching, okay, because you're considering different possibilities, okay, different moves and their effects and what the subsequent moves are, okay. By doing that, you're doing the search, yeah, because you're exploring your options. So adversarial search means that when you are doing a search to choose a move, you have to consider what the other side, okay, the other player will respond to what you do. There are many types of adversarial search, or for simplicity, let's just call them games. So we're going to talk about games, and of course, games are very popular in artificial intelligence research, popular for researchers, um, and of course popular for the observers of this research. Okay. A few years back, maybe around when you're applying, if you apply for the Department of Computer Science, okay, when you graduate from high school and you want to get into um, the department, okay, yeah, many of you in your application material stated that, oh, it's so much fun. I watched the AlphaGo with a master in the Go, okay, the game of Go. And that's so exciting and so interesting. Well, that's a game, and but it catches people's attention. Yeah, because game is actually very, I mean, it catches our attention because it's both fun and challenging. So yeah, games are very popular for artificial intelligence research. And of course, a lot of time, what we learn from games can be transferred to different domains of more practical purpose or practical use. Yeah. So games are good, and yeah, there are so many different types of games. For this set, when we talked about techniques, we mainly focus on what we call a two-player turn-taking deterministic zero-sum games with perfect information. Okay. So there are a few keywords here. Of course, two-player, you and your nemesis. Turn-taking, so when one is thinking, the other has to wait. Each one take one move. Okay. Deterministic means that what you do, yeah, completely determines the new state. There's no external and controllable factors that's in there. Zero sum means you win, then the other lose. Okay. Perfect information means you know everything in the game. Of course, that's true for some games. Although not every game, but many of the well-known games. And then after that, we'll talk about how to handle a few things. One is resource limits. The other is factor of chance, something that you cannot control. And games with imperfect information. Okay, these two are different. Imperfect information is just something you don't know, but that's different from something being stochastic. And then we're going to have a few slides covering some more recent developments. Okay. So we're going to start with some more classical method of gameplay AIs. Yeah, there are many ways to characterize games. A lot of things you see here are just board games. Yeah, board games are basically turn-taking games. Yeah, because at any moment of the game, only one player is thinking. I mean, that's the player's turn. So generally, we'll divide the type of these turn-taking games based on one is deterministic or chance. The other is whether you have perfect or imperfect information. So you see many different things here. Maybe some of the games you are already not so familiar because there are too many other games available today. Yeah, so you don't play them anymore. I'm not sure how many of you still know the game of H or game of F. Yeah, I've asked about that, and not many of you actually know it. Okay, but some, of course, are very well known. This is the Go. Okay, game of Go, the chess, and this is a bridge. Okay, this is called Chinese chess. Okay, and this is Othello. Some of this has perfect information and deterministic. Yeah, examples like, well, you can see everything on the board, like C and G. Okay, Othello, Go, those belong to this region. Okay, this square. If you have perfect information, but there's some chance factor there, okay, that means that the dice, that you have to roll the dice, that game on. Okay, you have to roll the two dice before you can take moves, and your available moves depend on the result of dice rolling. Okay, so that's a factor of chance. Imperfect information is that bridge. Okay, of course, this is from the view of onlooker, okay, not the player. The player cannot see what the hands, the cards in hands of the other players, and that is the imperfect information. Very similar like this, or oh no, this is not Chinese chess. This is Chinese checker. Chinese chess is 象棋. Okay, the dark Chinese chess, or somehow similar, is that some of the pieces are covered. Okay, those are also for the imperfect information. And then there's, of course, sometimes you have both. Okay, yeah. These are typical board games, and well, most people play these games. But I'm not sure how many of these you know of. Okay, of course, these are today's popular games. Some of them, okay, they're kind of different. I choose these games because those are games that my kids have played. Okay, so I know of them. Yeah, there are more games that I don't know of. If you don't know what these are, it's okay. Yeah, you can see whether you can find them. Yeah, but I think they are some of them are rather popular. Games like this are actually quite different from the board games because they are not turn-taking games. That means nobody waits for anybody else. Okay, even if you're not doing anything, the environment and the other players are still moving. Okay, things are changing and things still happen. Yeah, whether you do anything or not, no one is waiting for you. Okay. So these are not turn-taking games, and as a result, no, one of them is turn-taking game. Sorry, I put it here. It's a newer game, but it's not. It's turn-taking. Sorry. Maybe I should remove this one. It's a different one. Okay. Yeah. Maybe when I upload the slide again, I will put something else here. Okay. Yeah. Different from that one. Okay. But when you're not turn-taking games, you have some different challenges. Of course, it's not the only challenge, but that's a major challenge. That means you have to make quick decisions. And these games, usually they are continuous in time, which means that what you do at one moment has effect of many yeah, it can have an effect immediately, and it can have effect at some much longer time later. The reason that we say it's much longer time does not mean about the absolute time, like 1 hour or 30 minutes. It's not like that, but because the more continuous nature of the time scale, that means from one state to the next state, um, it's a very small time step. Okay. When you're playing a turn-taking game, each hand, or each move is like a time step. Okay. So things like this, they are only like from tens to hundreds of steps. Okay. As complex as Go is, okay, it maybe it's usually ends around 150 or 200 moves. So that's the number of time steps it can. Yeah. For something like this, because each time step is very small, you can say uh, like 1/10 of a second or 1/30th of a second, if your system has that kind of frame rate, okay, or maybe even faster or slower. But anyway, usually a game involves thousands or tens of thousands of time steps. Okay, so you have to process the states very fast, and you have to be able to handle things like appear many time steps ago, or will affect things many time steps in the future. Similarly, usually the environment is also more of a continuous nature. So that's also different from the board games. Okay. Yeah. We're not going to talk about the challenges here so much because it's a pretty different story. Although we're going to touch on that a little bit. Yeah. Maybe in more subsequent lectures in the semester, we can talk about some of the techniques used a little bit more. Yeah. So here, the purpose of this slide is just to let you know that there are many other games. Of course, you know that, but the challenges from these games are very different from what a typical perfect information or a typical turn-taking game is. So, in any way, no matter which type of game it is, we can always have a game definition. Because if you want to build an agent that can play in the game, it needs to know, yeah, what the game is like. So of course, there are elements in the game, and you have the initial state, you have the players in the game. Okay, you're a player, but there are other players. The complexity can increase a lot with the players. Players generally refer to any agent that has some kind of thinking or intelligence. Right? So if something just moves in the game, it has a fixed pattern. Okay, yeah, then it's not considered a player. It's just part of the environment. Okay, the environment itself can change over time, but it's just part of the environment. But a player here, that can include NPCs, okay, the non-player characters, okay, the NPCs. That's included as long as it has some capability of thinking and response to what you do. Yeah, that even though that can be simplistic, simplistic thinking, but that's still thinking. those are considered the players. Okay, like when you play the Pac-Man, okay, and they are the four ghosts. Okay, they are considered, the ghosts are also considered some sort of player or NPCs because they are thinking. Okay. Yeah. And then as a player at any game state, you have a set of available actions, and your action can affect the resulting game state. That's called the transition model. For a deterministic game, a transition model is, well, deterministic. So that refers to this. Okay, yeah. Terminal state. Of course, when the game ends, you have to decide on that. Utility is a function of the state, and of course, for which player, because if a player wins in a terminal state, the other player loses. Okay. That's real-sum games. So utility is the status of the game state, a function of game state, and with respect to a particular player. Yeah, that's just for the game definition. But for a player to have to make a decision in the game, what we need is a game search tree. Well, this semester we probably will not talk much about the search tree. Yeah. So here is just a very quick review about search tree from a particular state down. Yeah. So each search starts from the initial state of the search. Okay, so it's the state A here. Yeah, and you expand and generate child nodes. Okay. And then you pick one and you expand again. So to understand the search tree, the fundamental thing is that the tree grows as the search goes on. So it's the picture in your head should not be a complete tree. Okay, like what you learn in the course of data structure, you have a complete tree, and you start from some node, and maybe you want to find the path to another node, for example, like that. Yeah, but for a search tree, you grow the tree as you go. Okay, so the tree becomes bigger and bigger and bigger. So each iteration, you expand one node by adding its children to the tree. And each child comes from a valid move from that node. Yeah. So that's the iterative. Okay. That's one iteration. The other iteration, each time you have to choose a leaf node to expand. So different searching strategies or searching methods differ by how you choose that node to expand. So that's the basics of search tree. And what's important for a game tree search is that the root is the current state. Okay? So the root is not the initial state of the game. Generally, when you're doing search, you search from the current state. So for each move, you have to build a tree. You don't. It's not like you build a search tree for the game. Okay, the whole game. Yeah, that's not the case. You have to build a tree for each move. Okay, when you want to, you have to play a move, and you build a tree with the purpose to identify the best move. Which move should you take? Yeah, you have to decide on the best one. That's the purpose of doing that search. Yeah. So in the tree, each node has to keep some information. Okay. Generally, what you need is the state of that node. Also, you have paths or links to your children as well as link to your parent. The link to the parent, although not important for all the search trees, but for games, it's important. Okay, because the purpose of the search in a game tree is to collect information. Okay, think about what goes on in your mind when you actually play such a game. Okay, you are thinking about what if I make this move, then what the other player might do. Okay, and if he or she does this or does that, then what my response would be. Okay, and what the state of the game will look like. Okay, and you continue this process. Good and not so good players mostly vary on how much thinking can happen at this stage. Okay, yeah. A good player may be able to process many possibilities during a small amount of time, like a few minutes. Yeah, you process a lot of possibilities and try to determine the best one, depending on what will happen if you do that. Okay, so that's a tree search going on in your mind. As a result, the information are collected at bottom of the search, and they have to pass back because you want to make a decision on the information collected. So that's what's in each node of that game tree. As an illustration, most people will start with the very simple game of tic-tac-toe. Okay. Well, if you see the picture, you know what that game is. Okay, every kid has played it when they're little. So let's consider one player is max and the other player is min. Okay. Over here, the game tree starts from the initial state of the game because this is a very small game. Okay, even if you draw every possibility from every move, the tree still has a manageable size. The reason that we call it the max and min, well, will be explained when we talk about the min-max approach. Okay, yeah, you probably have learned about this in your previous courses. So yeah. Anyway, this is just a review. So how many nodes are here? It's not that difficult to estimate, right? To find an upper bound, you start from 9 and then there are 8, so it's fractal of 9. Okay. Think about this game tree. We have to make a move selection where we want to select a move. Okay, which one should I pick? Okay. Yeah. What you do is to find what might happen. So you look for all the paths. Okay. For example, how good is doing this? Okay. Press your first move at the top left corner. How good is that? Okay. So you have to. What you do is you can check the whole subtree starting from there, okay, and try to grade it, okay, get the score. And for this one, you can look at what will happen at the end. Okay, sometimes you win, sometimes you lose. Okay, it's +1 if you win, it's -1 if you lose. And you try to collect the information and see how good did this move. Yeah. For tic-tac-toe, it's possible to actually look at the bottom or the eventual terminal nodes of the tree because the tree is pretty shallow. Okay, At the most, you have 9 moves. Okay, the depth is 9. Yeah, for most games, it is impossible. Yeah, because the tree, if you want to have a game tree starting from the initial game state, and you want to all the branches to go down to a terminal state, and that's when the win or loss is determined. Okay, that's a huge tree. Right? Mostly because it's a large branching factor most of the time. Not for all the games, but for many games, that's the case. Um, a branching factor B is usually in the tens or 100, around 100 for example, a board game. Okay, yeah, it's up to like 300, around 300 for computer for Go, the game of Go. Okay, an example of chess is reasonable choices around 35. Of course, it's not a fixed value, so it's just around that. Okay, M is the typical depth. Okay, the number of moves, uh, total moved by all players to a terminal state. Okay, how many move? Okay, so around 100 for chess, maybe 150 to 200 around there for Go. Okay. So even for chess, that's a lot of nodes, and that tree is huge. That too big for you to actually grow it. So that's why those games are still complex. Okay? Complex for computers or for humans. If the game tree is very small, like tic-tac-toe, then we can solve this game by have the complete game tree. That way we can with the complete knowledge of the game tree, we can know the optimal move at each game state. Okay. With the optimal move, that means the game is solved. However, without that, we have to guess the optimal move from finite information. Imperfect. Okay, and we have to execute a new search every time. Okay, yeah, a new search means you want to explore part of the complete game tree, not just from a particular node, not from the overall root of the overall game tree, but your game search tree starts from one of the state, and you just want to explore the subtree there, yeah, instead of keeping the whole tree. Okay. So next is that we want to review the minimax principle of move selection. Okay. This is a classical way of doing gameplays, and for most game AIs, maybe before 2006. Okay. Yeah. Ever since there are game AIs in the 1950s up to around 2005, 2006. Okay, the minimax principle is the principle of playing this turn-taking zero-sum games. Okay. So that's what we're going to introduce here anyway. So consider a two-ply game. Two-ply means that this game tree involves only 2 moves. And after the 2 moves, you already have the utility function. Okay, the utility function is for the player who makes the move at the top. Okay, so from that initial state, one of the player has to choose from 3 possible actions. Okay. The utility functions are from the perspective, from the viewpoint of this player. Okay. Yeah, but as a 2-ply game, that means the other player also gets to respond to your moves with also some choices of actions. Okay. Yeah, so max, when it's drawn like this, max is the player making moves here, and then the player min will make moves. those are the resulting game states and their utilities. Of course, the purpose of max is to maximize the utility. The minimax principle means that each player will do what he or she considers the best move, right, for himself. What looks like optimal and worst for the other. So for your opponent, okay. Your opponent will definitely choose one that's worst for you. Right? Yeah, that's the minimax principle. So here, among those three moves, okay, if you choose the player here choose A1, okay, and the opponent will then choose what's worst for this player, and so number 3 will be selected. Okay, so that's why it's called min, because it chooses a minimum in terms of the utility for the player making the move. Okay, so similarly, 2 will be selected here, and the move for this, the D3 will also be selected here. So the player here should expect that if takes the action A1, then the outcome, the utility you're going to get will be 3. Okay, although there are no 3 possibilities, but based on the thinking of your opponent, what you're going to get is that 3, and that will be 2, and that will be 2. Okay, each of those will be the minimum, okay, the minimum here. So out of the 3, 2, and 2, because you want to maximize what you get, okay, so you choose the largest one, you take the max. Okay. So that's why the current player who's about to make the move is called the max. Take the maximum. So after introducing the min-max principle, yeah, that's what can be summarized in this. Yeah. So for each path, you determine the worst possible outcome. Okay. Each action, you determine the worst possible outcome. And then from those results, you choose the action whose worst possible outcome is actually the best among all the outcomes. Okay. Yeah. Yeah. So that means the minimax assumes your opponent is as good as possible. Yeah. Not always the case, but yeah, if you want to be able to play a good opponent and play that opponent well, then yeah, that's still a reasonable assumption. So that's the pseudocode for actually computing the max and min values. That is to propagate those things we just said, right? The game tree search is to collect information for the player to make a decision. So that's a process. It has to go through all the whole tree here, well, to the point that the utility can be determined. This basically is a depth-first search. Okay. The structure is depth-first search. Okay. It has 2 parts because it goes through max nodes and min nodes. Okay. So internally, one of it has to take the max, the other has to take the min. Yeah, that's the only difference, but the structure is a depth-first search. Okay, so that's for minimax search. Yeah. It's reasonable, but it's not the most efficient because there's some waste that we can observe in the search. Yeah, as I just said, minimax search is the fundamental of game AIs. Okay, at least for the turn-taking game AIs for like 50 years. Okay, is fundamental of that. So there are many modifications, amendments to the basic algorithm there. Yeah, too many to actually discuss. Okay. But one of the most useful is called alpha beta pruning, which is a reasonable way to reduce the waste. Of course, you want to reduce waste because the complexity is very large. Okay. You're doing depth first search, so space complexity is not a real issue. Okay. During your search, you do not need to remember everything in memory. Okay. Eventually, you just want to choose a move. So it's not necessary to remember the whole tree. However, time complexity is an issue. It's B to M. Okay, remember B is the branching factor, and M is the depth to the terminal state, or it is the depth of search. Yeah. So some of the waste happen that some branches actually do not need to be checked because you're sure they won't affect the result, the final decision. Okay. So the illustration here for this, okay, this is the selection of that minimax tree, okay, written in one expression here. So those are the three min nodes, and there's the max nodes. Okay, and eventually this will choose one that's the three here. And the result selected here is the same as the result selected here. Yeah, think about this. If I remove those two, or just ignore those two, I still get the same result because that's the minimum already. That two is already smaller than 3. Okay, yeah. So I already know whatever I can compute out of this, it has to be at most 2, and the result is worse than what we get here, and so it will be discarded. Or, yeah, so those do not have to be checked. Okay, and in reality, those are not just single nodes. Each if you go more than 2 price, okay, or each of those is actually the head of a subtree itself. So the saving can be actually quite significant. Okay, you're pruning away whole subtrees. So this is called alpha beta pruning. The idea is that alpha it keeps the best choice for a max node, and beta means you pick the best choice for a min node. Okay, that's the value of those alpha and beta. The best choice of min nodes, of course, is worst, the worst choice for max nodes. But min nodes, the player min, is making that decision there. Okay. Well, of course, alpha is only used when there are internal max nodes. Like if you have a 4-ply search game tree, okay. Here we have only 2 plies, okay. So you won't see the effect of alpha. Anyway, yeah, you won't cause pruning. Okay. But if you have 4 prides, for example, max and min, okay, so for those min nodes, the pruning by beta can happen. And then there will be another layer of max nodes, okay, because that's the action, the move of max. And you can do pruning by alpha there. And then there's another layer of min. Okay, so more on the pruning of beta. So this can be applied to any of those internal nodes in the game search tree. So the alpha and beta are paced up and down. Here the bell, so we'll have a few minutes of break here until 2:20. Okay, we'll come back at 2:20. I'm going to stop the recording for now here. Okay, we'll continue with today's lecture. Okay, okay, the recording will be started here. Yeah, so we have covered alpha beta pruning. This is the pseudocode. Basically, the alpha and beta values, because it has to be passed from branch to branch. Okay, so when you return from a depth first search, you have to pass that alpha and beta values back, so that when you are checking another branch, they can be used. This is the illustration, okay, from the game tree, that two-ply game tree we just saw. Yeah. This is the first time, the first path down. Okay. Here, we find the 3. So the 3 at this point is the minimum. Okay. The minimum is the best value for the min node. So at this point, it's 3, okay, the current best choice. And it finished this branch, it's still 3. So that 3 is passed back, okay, so that it can be used when doing the branch down, okay. Yeah, when you're going down, that 3 becomes the best choice of max. Yeah, the best choice of max. So you see, that's the position of beta when it's the best choice of the min here. But now for max, that max nodes is the best choice of max node. So 3 becomes part of becomes alpha when it starts another the search of another branch down. Okay. So the 3 here, and it finds a 2 at the end of this search. Okay, at the end of this pass. Because 2 is smaller than 3, so the pruning here is that, say that C is definitely worse than the current best one. Okay, yeah, because basically you want to continue the search only if you have some chance that the result of that further search can be better than the current choice that you have already know. Okay, if you are sure that further search will not give you anything better, then basically you can just skip that part of the search. So that's the case here. Once it finds that 2 here, it's sure that the whole branch will be worse than the 3 you already know. So basically that will be pruned. That means you don't need to check those anymore. Okay. Yeah. Yeah. So then it goes down, and again here, that 3 as alpha has to be passed down, because so that it can be compared with the search results here. And after this part is done, finished, okay, the minimum here is 2, so it's still worse than 3. Yeah, so that's the alpha beta pruning here. Well, here one thing we can note is that for this branch, okay, let's get okay, or maybe easier here. For this branch and this branch, okay, they both have a minimum value of 2. Okay, but the pruning only happens here for this one, but not here. Okay. The reason is that the pruning only happens when you see that when you find that the minimum value for that node, the min node, okay, it's already smaller than your current alpha, okay, the current best choice. Okay. If the so it can only happen for branches that after the value that's smaller than that 3. Okay. So when you see the 14, you cannot prune it. Okay. Of course, 14 cannot be selected because the best one is 3. Okay. Yeah, but 8 may or may not be selected depending on what happens following it. Yeah, but anyway, if you see 14 and then you see 5, at that point, I still feel that further search may eventually find out the minimum of them and whatever. Yeah, it hasn't seen the 2 yet. So what you don't know yet, you think there's a chance that this whole thing will be better than 3. So that's the reason that there's no pruning that happens here, but there's a pruning that happens here. Okay. Yeah. So that pruning or not pruning depends on the ordering of the nodes. Okay, because there are different choices that you have to check. So the order you check them affects how you can whether you can have the effect of pruning. Okay, so this gets us to the next point here. We want the optimal situation of alpha beta pruning, that all the nodes are ordered in the desired way. That means for action of min nodes, you start from the smallest one. Okay, like that 2, 4, 6. So the small ones are in front. Similarly, if you're doing the max node, then the largest one should be you should start with the largest one. Okay, so that has the most choice of doing pruning. Well, that's node ordering, and that can give you the best result, best saving, the most saving out of alpha beta pruning. In the optimal case, when all the nodes are properly sorted or arranged this way, then the complexity is this. Okay. Yeah, it can be proved, although we're not going to do that. But this basically means that the depth is the effective depth is only half of the original. Yeah, remember originally we have that b to the m, and now we have that b to m divided by 2. Okay. As a result, for the same amount of resource, okay, you can actually go twice the depth. Okay. For example, from 2 pi to 4 pi. Originally, you can only do 2 pi's, but right now, in the same amount of time, you can do 4 pi's. Okay. A 4 pi search usually is much stronger in terms of the game AI. Okay, that game AI will be much stronger than like 2 pi search. Yeah, just think about how good a human player, if you can think about 4 moves down, okay, 2 by you, 2 by your opponent, 4 moves down, right? That you might think that's actually a pretty good experienced player. It is not an amateur. An amateur maybe just 1 or 2 plays, 2 moves. Okay. Yeah. So that's a strong increase in the stress. Okay, it's not half of your computation. Okay, a factor of 2 is no big deal, but a factor of 2 is depth, because this is like taking the square root. Okay, yeah. So a factor of 2 in the search depth translates to a huge increase in the strength of that AI. So that's the success brought by the alpha beta pruning. Now, Of course, the problem that we are left here is that's the result of the optimal case. That means all the nodes are actually optimally ordered. However, how are we going to order them before we actually do the search? Okay. Because actually we don't know those utility functions yet. We're not just reaching the terminal state. Yeah, we're doing 2 ply, 4 ply. Those are not terminal states. So how do we get the functions, the values, the utility values for us to do the node ordering? Okay, so we need some estimation. Okay, the estimation of the value or the expected utility of a node. That's called the evaluation function. Okay. It's important for the game AIs. For any game AI that's play a game where you cannot have the complete game tree. Okay, evaluation is fundamental because without the actual game tree to the bottom, to the terminal states, you still have to be able to estimate how good a node is. Okay. So here we can do the node ordering for arbitrary pruning using the evaluation function. However, evaluation function goes much beyond. Okay, its role is very central to these game AIs. Okay, not just for classic game AIs, but for today's most sophisticated ones as well. Okay, like when you talk about AlphaGo, okay, evaluation function is still the core of it. Okay. Yeah. So generally, the need of evaluation function comes out of the difficulty to cover the whole game tree. Okay. So for any reasonable game tree search, we cannot reach the actual terminal states unless you're playing something like tic-tac-toe. Other than that, it's difficult to get to the bottom of the game tree, of the complete game tree. Okay, so your search has to stop somewhere. Okay, like 2 plays out, 4 plays out. Okay, or 8 plays out. Okay, if you can do 8 plays out, usually means you're a pretty good, experienced player. Yeah. Okay, so this kind of thing is called the cutoff test. Okay, yeah, you cannot reach terminal state, so you have to cut off somewhere, and in that case, the estimate, because you don't have the exact utility function there, so they're replaced by the evaluation function, okay, which takes a position and help. The purpose of evaluation functions is to allow you to still make an intelligent choice of action. So you want it to be a representative of the goodness of a state. And it has to generally, we want it to be able to evaluate it from that state directly. Yeah, because you want to save the time for a search, a tree search. So yeah, before you go down tree search, you want the estimation. That's the evaluation. Okay. Yeah, and people have developed evaluation functions for some games. Yeah, because usually some of them can be pre-summarized with rules. Yeah. They're not perfect, but they have good enough correlation that in some way can predict the probability of winning the game from that state up. Evaluation functions are not part of the game rules, okay? But they are useful for a player. Yeah. they come from expert knowledge or from past experiences. So if you play a game enough times, you gradually learn something about what may be good, what some state or some configurations are good, some configurations are probably bad. Yeah. Those will factor into your evaluation functions. And if you want to learn some game real well, okay, yeah, then you have to probably memorize some of these things. Yeah. Yeah. So the classical way of building a game AI, okay, a game playing AI system, is to use the minimax algorithm, okay, and you add in alpha beta pruning, and you add in the evaluation function. So that's the core. As I just said, that's the core of game AIs up to like 2006. And what you can improve on, maybe a little bit efficiency of your algorithm so that it can try to go deeper. Okay, do more search or focus your search on the most promising path. Okay, yeah. If you don't want to explore everything in the subtree, then you have to be able to choose part of it that seems more promising or more important for you. Okay. So there are many techniques for that purpose, to make the most use of the time taken on doing that game tree search. But they're all built upon that minimax search. Yeah. And of course, among those methods, the most successful and most useful one is alpha beta pruning. Yeah. On the other hand, the evaluation functions themselves have to be built up, and for a complex game, the evaluation functions can be complex as well. Improving evaluation functions is like improving your experience. Okay, you know more about the game, you have better idea about what's good or what's bad, and those lead to some good results. Yeah, this has been there, but yeah, the only problem is when the game is real complex. Yeah, like Go, right? Yeah, then it's not sufficient. Right? But chess in a classic example of the development of game AIs. So generally, examples start with chess. So if you are not familiar with chess, it's okay. There are a few different types of pieces in chess, and well, they have different values. So some are more useful than the others. Yeah, or at least you have good idea about Chinese chess. That's good as well. Okay, and piece counting is a simple way of evaluation function. Okay. So when doing piece counting, you ignore their locations. You just count how many pieces players still have. Okay, and assign different weights. Yeah, because different pieces, different values. So you assign different weights to the pieces. Okay. So in this case, very apparently the black is in a better position. Okay. So those are just different values for the different pieces. And those of you who are familiar with chess will know that the queens are the super valuable pieces there. Okay, where are the queens? Okay, that's a king, that's not the queen. Okay, the queen is here. Okay, that's a white queen and the black queen. For this side, it's just to mention one of the issue that because we can only do depth limited search, so sometimes we cannot know what might happen. Okay, yeah, maybe the bottom of the search is a state that's appear pretty normal, a harmless state, but it will lead to something that's real good or real bad. Yeah, but because of your limited depth, you cannot know that. So the example here is that that's a king, okay? That's a king. So this configuration is somehow different from this one because white rook is actually shoot the spot. Okay, and well, if you're just counting the pieces, these two will have the same values. Yeah, because they are the same set of pieces on the board. But for this one, well, the next play, black loses. Yeah, because the rook captures the king and the game ends. Yeah. So some of the cases, you yeah. So there's something that in some cases you have to check a little bit more. Okay, so that's the purpose. Okay, yeah. So some of the moves, not all the moves have to be checked further down. Yeah, but it has to do a little bit more search if some move or the immediate subsequent moves can have a huge effect, like a capture. Okay, or like this, it ends the game. Okay, so yeah, just focus on some of the most important moves and just to check a little more. And there are some others, yeah, like singular extension. Yeah, it will choose out of the many diff nodes in your depth limited game search tree. It will choose a subset, a small subset, yeah, that looks most promising for you, and then you do very long search, going down very deep. That's called a single extension. And then there's the forward pruning. Yeah, it's just like you should call that bin search or something like that. Yeah, so you kind of limit the number of the nodes at different levels. So that it won't grow that fast, the game tree size. Okay. Again, you have to choose the better ones for the current player. Okay, so the comparisons or the selections are made usually you can have rules, but more often by evaluation functions. Okay. So those two and that consent search as well, they are all intended to for the more important or more promising subtrees, you want to go somewhat deeper, yeah, to check them out. Not all the subtrees, yeah, but some of them. Then the next one, the transposition table, is a different way of improving efficiency because usually it's just like somewhat like VCS states. Yeah. Like when you're doing the Dijkstra algorithm or some of those graph searching algorithms, okay, you have to check whether a vertex or a node has been checked before. Just something similar to that. In a game tree search, it can happen very often that many paths, okay, down the search tree actually have the same state. Yeah, and they just come from different ordering of moves. Okay, yeah, you just think like you can move right and move up to reach a step in two moves. Okay, or you can move up and move right and you reach the same state. And in that case, it's meaningless to repeat the search out of that new state. So that's transposition table. The purpose of transposition table is for you to remember some of those things so that you don't waste the time on those searches. Okay, those searches happen on different subtrees or other different nodes of your game search tree, but they are the same thing. And finally, usually then this is based on what professional players would do or semi-professional or just experienced amateur players would do, is like how to start the game or open the game and how to end the game. Variations during the opening or during the end game or the game complexity are less than what the game looked like in the middle of a game. Okay, yeah, because during the opening, very few pieces are actually moved or added to the board. Okay, so mostly most of the pieces are the same. Okay, yeah, so that's the case of opening. And for end game, usually also there are fewer options for you to do. Either you have fewer pieces like in chess, or you just have fewer places that's meaningful, like in Go. So for those things, with the reduced complexity during the beginning and end of the game, it's possible to use a database, okay, to collect useful experience about what you can do there. So those are done by actual human players, in many of the important games, and of course that can be learned by computer AIs as well. So in those cases, you can do lookup. Okay, like you have a lookup table. People have tried to especially make endgame database. Yeah, about what will happen if you have, for example, in chess or in Chinese chess. Okay, when you're down to just say 5 pieces or 6 pieces left on the board, that means 5 or 6 overall. Okay, 2 players pieces combined. All right. So when you have just very few pieces left, then the complexity is small enough that you can build complete game tree out of those states. Okay. Not the original game, but just the end game. Yeah. And for opening, the part of opening, usually how to start the game, those are usually taken from experience of human experts. So so far that's the discussion of the basic turn-taking games. Turn-taking games with that's deterministic and perfect information. Um, let me see. Should I go a little bit more? Yeah, let's go a little bit more. This is a stochastic game. I know very few probably have played this. Yeah, but they are it can be easily found online. You can play against people from other countries. So if you're interested, you can try it. Okay. So basically, the purpose of this game is for the 2 players to move their pieces around to the other side. Okay. The player who finishes this first wins. Yeah. And the rule states that what actions you can take depends on the dice roll. Okay. You have 2 dices. And that depends on what you can do. So in the rule of the game, vector the two dices can give you 21 combinations, I think. Yeah, because 1, 2, and 2, 1 are the same thing. To represent such a game tree, because what the valid moves depend on the result of the dice roll. Okay, so the dice roll itself has to become a layer of node. Yeah. Because the reason is that the passes, okay, the passes are, or the branches, they have to be valid actions, and the valid actions depend on the result of the dice roll. Okay, so the dice roll itself has to be a layer of the nodes, okay, so that all the branches are possible. Although in reality, what happens, okay, those are what happens, okay, includes the dice roll that for this part, you can call the chance node, because for this part, it's not something that you can decide. Okay, that's something that you can decide. It's the dice. And for the branches, basically each branch out of the dice roll has a probability, because different configurations have different probabilities. So the whole game tree will be something like this. What you see is that that dice roll belongs to me, okay, because for you, the player making the decision, okay, this is after you already rolled your dice, all right. You have to make the decision after you roll your dice, okay, so that's something you have to do. And then the chance node, that's for me, the opponent, okay, yeah. So that's for the opponent, and that's for your next move, okay, chance node, and then you select an action. The evaluation with the probabilities, you cannot take the mean and max, okay. For a normal human player or AI intelligent node, okay, max or mean, it takes max value or the mean value with the min-max principle. But for chance nodes, well, the only reasonable thing you can do is probably to take some weighted average, right? Weighted by the chance or probability of that node, okay, of that result. So that becomes expected utility. Okay. I'm not going to explain much about those numbers. You can look at those yourself. But that's the idea here. Generally, stochastic games have very high complexity if you just consider player moves. And the reason is because of the chance nodes also have a large branch factor. Yeah, like the gamma, I just said the branching factor of the chance nodes is 21. And the result is very difficult to go deep, okay, into the game tree, yeah, because of that added complexity. And also, as a result, at some level, like 2 moves down, for example, there will be a huge number of nodes. Yeah, just like 2 moves down. Okay, when you say 2 moves down, it's like this. Okay, that's 1 move. Okay, that's the other move. Okay, down to this here. Okay, so the number of nodes in this layer is just very large. And with that number, actually each state has a very small probability to actually happen. As a result, statistical games usually do not have deep game trees. That kind of search is not really useful or meaningful because many of the search results won't happen at all. Yeah, when you are computing expected values of something of chance, it's not that useful to do the min and max below that. So these trees tend to be shallow. For example, the TD Gammon is a very famous program for the game of backgammon. Okay. The TD is terminology of reinforcement learning, so we're going to talk about that. Okay. But anyway, at this point, I just keep the name here, the TD Gammon. Yeah. It can play at the level of a human world champion, but the surge is only like 2 pride or to 3 pride. Okay, 2 moves down, or maybe it's max min max, or one more layer max min max min. That's about it. Okay, and the play actually depends on evaluation function learned from playing. Okay. That's the key, and that's still, as I just said, that's still the key today for today's best game AIs. Okay. This game AI still have to depend on evaluation functions, but the evaluation functions can be better and better, and for you to choose what's best. Right? Yeah, very good evaluation functions, and of course you want very good evaluation functions for complex games. Then they have to be complex and sophisticated themselves, the evaluation functions. So in some way, TD Gammon has some evaluation function that's depend on neural networks. Okay, although it's at the time before what we call the deep neural networks or deep learning today, but that's how it works. And for today, of course, we have really huge neural networks that acts as the evaluation functions, which can be learned from a very large amount of experience. So that's for the stochastic games. Okay. For the lecture part, I think I'm going to stop here, and the rest of slides will be given next week. We have a few minutes left, so I will give you a chance to post questions related to the project announced this time. Okay, I know some of you have sent questions through E3. Right? Mostly that's about the data sets. Okay. So generally speaking, the important thing is for the first data set that I said you have to compose yourself. Yeah, I want you to actually do it. Yeah, because that gives you experience when you have to think about how you compose a data set. You have to think about the classes, the distribution, and what kind of labels are meaningful. Okay, sometimes those things are not that straightforward, and you have to learn to document your data set. Yeah. How you compose it, how you choose the samples, and how you label them to document that data set. Okay, so yeah, the idea is that I said 3 data sets, right? So the other 2 you can get from public data sets made by others. But for one of those, I want you to know the process of actually building one. Okay, so that's the question we've got, and any other question, about the project can be posted on the message board. Also, another announcement is about the groups. Okay, because following this, we're going to, next week, we're going to announce the game project. Okay. Yeah, and those will be done with groups. So the idea is that you should start forming your groups now. After today's class, I'm going to put a discussion board, okay, a discussion topic on E3. Okay, now there are discussion topics, and you can post on those. Okay, generally that's for questions, but for that one, please post the groups there. Okay, and if you are someone who you need to find a group, you want to find a group, but you don't know who to ask, then you can also post something like, oh, please, I need a group. Do you have space? Anyone has space? That kind of message is okay too. Yeah. Eventually, I hope that within 1 week, at most 2 weeks, but I hope it's within 1 week, it is all of you already have groups. Okay. Well, number of persons in the group is 1 to 3. Okay. So the upper bound is 3. Too many people in a group is not so good because that usually leads to someone who has basically nothing to do most of the time. Okay, so I don't want to have big groups. Yeah, for the project because it's more about actual implementation and experiments. So the small group size is okay. And the lower bound is 1 means that although I do encourage groups, work in groups, but if you just feel you like to work on it yourself, yeah, if that's your preference, and I know that's not too uncommon in a department like this, then that's okay as well. Yeah, you just specify that you have only 1 person, and that's a group. Also specify that in the department, in the discussion board. Okay, yeah, so that yeah, me or the TA will not try to get you to some other groups. Okay, so that's all for the announcement today. Yeah, yeah. So if you have questions, again, questions, press in the message board on Google Meet here. If you have no questions, then this is end of today's lecture. I'm stopping the recording here.